We are told that a real gas obeys this equation of state, and it experiences a certain change in state such that its temperature and pressure is changed from 300 Kelvin and 4 atmospheres to 400 Kelvin and 12 atmospheres. So that's the change in state of the gas. We are tasked to calculate the change in its entropy for this change in state. This problem suits the use of the calculation of a change in entropy using this equation where ds is expressed in terms of temperature and pressure very well. So we can now choose any convenient path. We can say let's keep the pressure constant first, and then we evaluate this part where the temperature changes, and then we change the pressure while keeping the temperature constant, and we use this second path. Or we can decide to keep the pressure constant first and then evaluate the change in pressure, and secondly the change in temperature while we keep the pressure constant. However, the true nature of the problem is revealed if we consider the information that we have about this gas in terms of its physical properties. We know its mean Cp value at 1 atmosphere. So Cp refers to a change in temperature under constant pressure conditions. So there's a restriction in the path that we can actually follow. In other words, we can only evaluate the change in temperature part of this equation at a pressure of 1 atmosphere. So whatever path we design, that is where we can account for the change in temperature. So we are left with no other option than to first reduce the pressure of the gas to 1 atmosphere in step 1 of our path, change the temperature at the pressure where we have the Cp value available, and then finally increase its pressure to its final value. The whole purpose of this example is to make you realize that we should maybe sometimes think out of the box when we consider the path that we use to calculate a change in state variables. This therefore corresponds to this process scheme that's set out here. First, we are going to keep the temperature constant, evaluate the change in pressure from 4 atmospheres to 1 atmosphere. That's our step 1. In step 2, we can now change the temperature while the pressure is constant. So therefore just this part of the equation would apply. And then finally, we can calculate what happens to the entropy if I change the pressure to my 12 atmospheres, but now my temperature, whenever I have to substitute the temperature in whichever equation results from this slope, remember that it should be at temperature 2, where I am currently when I evaluate that portion of the path. So let's start with the two portions of the path where we are going to change the pressure while we are going to keep the temperature constant. This is step 1 and step 3. For both these sections, we are going to be required to evaluate this expression in order to calculate the change between the beginning and the end state of each, and therefore we are going to integrate whatever expression we get here from the pressure at the beginning to the pressure at the end. Subsequently, we need to get an equation for the slope of ours by considering our equation of state. Therefore, we need to make volume the subject of the equation so that we can differentiate with respect to temperature while keeping the pressure constant. So you can check my maths on your own at your own leisure and see whether you agree with the equation that we get for the slope. This can now be substituted in there, multiplied with the negative sign, remember. So now we can just integrate between the appropriate boundaries in order to evaluate the delta S for step 1 and step 3. I do not want to spend too much time on the maths, But I want to point out one important aspect of this evaluation that is missed by many students when they do problems in TATS or in tests. And that is, if you consider this expression, this is still general, this. And we can apply this equation now, whether we are considering this first part of the change in pressure or the second part. What changes is that this part, first part, occurs at 300 Kelvin, whereas this final change is 400 Kelvin. And that is important because in this evaluation, therefore, for step 1, we have to substitute where the temperature features in this equation. It's a constant temperature, it's not an average, it is the temperature at which that step takes place. Now that we know the value for the change in entropy for step 1, evaluated at 300 Kelvin, we can calculate the change in entropy at 1 atmosphere due to that change in temperature from 300 to 400 Kelvin. So for the last step, step 3, we can apply exactly the same equations that we derived for step 1, except that now the slope needs to be considered at 400 Kelvin, and we can get the answer for that final step. Total can then be calculated as the sum of all 3 steps. Please note the sign of the delta S values and make sure that it makes sense to you that when I experience an increase in pressure, a constant temperature, a decrease in entropy is observed. Make sure that the signs that you get for the changes in entropy for step 1 and step 2 make sense to you as well. The second part of the problem wants us to estimate the mean CP value at 12 atmospheres. For a high-grade question, this would be the only question asked without prompting you to first calculate the change in entropy between the given changes in state. At this stage of the problem, we know what the value of the entropy change is for this gas between a state at 300 Kelvin, 4 atmospheres, and 400 Kelvin and 12 atmospheres. So we can now design a path, step 1, step 2, in which the entropy change in step 2 is the unknown, since 1 plus 2 must be equal to that total value that we calculated previously. If we can now calculate this unknown entropy, we can relate that to this part of the equation, the CP ln temperature 2, temperature 1 at 12 atmospheres, and we can calculate the CP value from that relationship. So the same expression can be used as that one derived previously for change in entropy with a change in pressure when the temperature is constant. Remember, in step 1, the temperature stays constant at 300 Kelvin, and that is therefore the temperature that we need to substitute in that part of the equation. And now we can calculate that missing CP value, because we know that the total entropy must still be the same as calculated from the previous path.